Good day. We are just some miles away from our training, principle and application of spectroscopy being organized by the Noble Minds team. My name is Samuel Adegboyega from the Department of Pure and Applied Chemistry, Ladoke Akintola University of Technology, Ogbomoso. My task is to discuss the UV visible spectroscopy under the outline with the outlines, principles, Woodward-Fisher rule, interpretation of UV visible spectra, and the other part, nuclear magnetic resonance. That's part 2. We shall be talking about the principle, the proton NMR, and the carbon 13. Let's look at the figure above. You will see the incident light which was made to pass through matter, and part of the light will be absorbed while part will reflect back. The part of the light will be scattered, part will be transmitted, emission, as you could say, and some will result in photophysical reactions, which is photoluminescence. So spectroscopy is the study of interaction between lights. We are referring to electromagnetic radiation here and matter, and we all know that matter consists of atoms or molecules, so to say, and with the intention or goal to determine the structure of different compounds that are present in the matter. Electromagnetic radiation is a form of energy which is produced by movement of electrically charged particles traveling through a vacuum, and the electric and magnetic field, they are right angle to each other. Let's look at different examples of electromagnetic radiation, as we used to know that we have radio waves, microwaves, infrared waves, visible region, ultraviolet radiation or rays, you may call it. We have X-ray, X radiation, or gamma ray. You have their wavelength as well as their frequency above. Let's go down a bit and look at the formula below. You see C equal to frequency multiplied by lambda, or that is a wavelength. So C is the speed of light, which has a value of 3 times 10 raised to power 8 meter per second, and the sign that looks like V here is a symbol for frequency of radiation, where lambda is the wavelength of radiation. So let's look at this formula. E equal to HV, or H frequency, and we know that frequency from the formula below, or before this, we know that frequency is equal to C over lambda. So we can find the relationship between the wavelength of absorption and the energy. So the energy of electromagnetic radiation being absorbed, the higher the energy, the lower the wavelength, and you see the Planck's constant with that value. We have different types of spectroscopic technique, and the type you apply depends on the nature of energy transfer between light, well, you may also call it photon, and the matter. And we have a table here which shows the spectroscopic techniques, different techniques that involves energy transfer between photon and matter. So you have energy transfer. What's the nature of energy transfer here? Absorption. And depending on the region of electromagnetic spectrum where they absorb radiation. So if it absorb at the gamma radiation, if it absorbs a gamma radiation wavelength, the spectroscopic technique that you will use for that is Mossbauer spectroscopy. If it absorbs at the region of X radiation, we have X-ray absorption spectroscopy. For UV visible, you have UV visible spectroscopy. For infrared, you have infrared spectroscopy as well as Raman spectroscopy. If in the microwave, you have microwave spectroscopy. Then in the radio waves, which we shall be talking about later, we have the electron paramagnetic resonance. It's also known as electron spin resonance spectroscopy. Then we have our interest topic, nuclear magnetic resonance spectroscopy. If the nature of energy transfer is emission or thermal excitation, and it absorbs in the UV visible region, you have atomic emission spectroscopy. If it is photoluminescence, you have X-ray spectroscopy, and so on, like that. There are other methods, or there are other spectroscopic techniques that do not involve energy transfer between photon and our sample, or the sample you want to analyze. So we show the region that the sample may absorb light and the type of interaction. If it is a diffraction, you have X-ray diffraction spectroscopy. If it is refraction, you have in the UV visible region, you have refractometry, scattering nephelometry, and so on, like that. Let's look at basic components of spectroscopic instrument. Virtually all spectroscopic instruments must contain these four components. It must have source of energy. So the source of energy, it could be electromagnetic radiation, it could be source of thermal energy, it could be a chemical source, depending on the method or technique. Yes, it must have a wavelength selection compartment. So we have you can select your wavelength using monochromator. You can select using filters or interferometer. And after that, it must have a detector compartment, as well as the compartment that will process the signal, which is a signal processor. Let's go straight to UV visible spectroscopy. UV and visible, now we have combined two regions now. Okay, is an electronic spectroscopy, which is used for detection of functional groups. Okay, functional groups there are referred to as chromophore, multiple bonds, conjugation, and aromatic conjugation within a molecule as a result of electronic excitation. So there are various or different applications of UV visible spectroscopy. We have functional group determination, extension of conjugation, and we have so many of them as are listed below. The principle of UV visible spectroscopy is based on absorption of UV visible radiation within the wavelength range of 200 to 800 nanometer by atom or molecules. Now, some resource material may give you a value around 180 to say 780 nanometer, so it's still within the range. So when they absorb light within that range, it results into something which we know as promotion of valence electron, okay, or say electronic excitation from lower energy level to the higher energy level. We have shown us the formula, the relationship between energy, Planck's constant, and frequency in the previous slide. So the formula that relates the lower energy and higher energy is given here. Now, the instrument which is being used for UV visible spectroscopy is known as UV spectrophotometer, UV visible spectrophotometer, and the working principle follows Beer-Lambert's law. So let's talk about Beer-Lambert's law. Beer relates the absorption to concentration of solute, and Lambert relates absorption to optical path length. So the two propositions were combined together, and they are known as Beer-Lambert's law. So, and it states that the amount of energy absorbed, photon, okay, in form of photon, absorbed or transmitted by a solution is proportional to the concentration of solute and optical path length. So if you look at this equation, A equal to log I naught over I equal to ECL. So you may just go and say A equal to ECL, which is also equal to minus log T. Or if you check from your indices, you know that minus log T is the same thing as log 1 over T. Okay, so if you want to check the relationship between the incident light, the intensity, which is I naught over I, and the transmittance, which is T, you find out that transmittance is equal to I over I naught. If you want to take the percentage, you multiply that by 100. Look at the figure here. You see the incident light. The intensity of this light is higher. It is made to pass through a convex air. Okay, this convex has a path length called L, and after the matter has interacted with the light, you see the intensity of light being transmitted or being released is very low compared to the intensity of light that enters into the sample. So that is the interest of Beer-Lambert law, and that is the principle that UV visible spectroscopy operates on. We have different types of electronic transition and their wavelengths as given below. There are actually more than this, but we just give a few examples. You can have a sigma to sigma star transition. The wavelength will be below 200 nanometer. And example of molecule which shows such is the molecules which contain saturated bonds, single bonds. We can also have N to pi star, that is non-bonding to, to sigma star, that is non-bonding to sigma star transition. You have the wavelength, you have to pi star, pi to pi star, okay, and you have different functional groups on that region, and you can also have non-bonding to pi star. So let's look at energy profile. You could see, we say between carbon-carbon single bond, the saturated bond, we have sigma to sigma star. So see, you can see how wide the energy, the band gap between the sigma to sigma star. Okay, and you check the one that absorb with a pi to pi star transition, involved pi to pi star transition, you see the energy reduces. Okay, the aldehyde functional group has pi to pi star transition, non-bonding to pi star transition, and non-bonding to sigma star transition. So if you look at that very well, you discover that the energy difference is reducing, okay, but something is happening there. The wavelength is increasing. So that correspond with the formula where we have energy equal to hc over lambda. We say that energy is inversely proportional to the wavelength. So the higher the energy, the lower the wavelength. And when the wavelength increases, definitely the energy of absorption will reduce. And let's still look at a conjugated bond. A conjugated bond here. You will see that the transition is between pi 2 to pi 1 star. So if you check on the x-axis, you are moving towards right, the wavelength is increasing. So that has a higher wavelength. But what happens to the energy? The energy band between pi 2 to pi 1 star is very small. So the higher the energy, the lower the wavelength. And the higher the wavelength, the lower the energy. That's the relationship between them. Let's go to terminologies that are used in UV visible spectroscopy, which they are important terminologies that should be that you should take note of. We have chromophores. They are covalently bonded unsaturated functional groups. Okay, they are the ones that are responsible for electronic absorption. So if you look at it, they contain essentially of non-bonding electron or pi electron, and we give examples of such compound. We also have another terminology which is oxochrome. This one, they do not have absorption of their own. What they do is that if they are attached to a chromophore, they tend to influence the intensity or the wavelength of absorption of chromophore. Okay, so we have example of this. Another terminology is a bactochromic shift, which is known as redshift. It simply shift to longer wavelength. Okay, and you know that the longer the wavelength, the lower the energy. Okay, we have hypsochromic shift, which is blue shift to a shorter wavelength. And what happens to energy then? Okay, the energy will be higher if the wavelength is short. We also have hyperchromic effect that is related to intensity of absorption. So it is related to increase in intensity of absorption of molecule. We also have hypochromic, that is decrease in absorption intensity. Well, you have some terms here. There's some acronyms. HOMO, highest occupied molecular orbital. LUMO, lowest unoccupied molecular orbital. Let's talk about effect of medium. So if you look at this in basic medium or alkaline medium, so to say, it increases conjugation. Okay, there's a negatively charged there that when delocalized into the ring, it forms double bonds and it circulates like that.